These are the answers to homework 4D. Here are the definitions I would like you to know. And now let's go to the questions. Number 1, if a combustion reaction is thermodynamically spontaneous, how does the paper of a book survive being in contact with atmospheric oxygen? And the answer is that the paper is stable due to the kinetics of the reaction because a high collision energy is required for the combustion reaction to actually start. So if the paper are the reactants and the paper with oxygen are the reactants and you want to turn it into carbon dioxide and water, then you need to provide a significant amount of energy for the molecules of paper and oxygen to collide with each other. And that amount of energy is so high that the molecules of oxygen at room temperature on Earth don't have that amount of energy. And so the paper therefore becomes stable. And we say it's not thermodynamically stable, but it's kinetically stable. Question number 2. For the reaction 2ClF3 goes to Cl2 plus 3F2, assuming the reaction vessel starts with only ClF3, sketch how the concentrations of all three will change versus time until the reaction reaches equilibrium. So for this reaction, we're going to draw a graph for the concentration of the reactants and products versus time. And initially, all we have is ClF3 in the container. Its concentration is going to wind up going down with time. And the amount that it goes down will be twice as much as the amount that Cl2 goes up. There's no chlorine to start, but as the reaction proceeds, you'll create that. And you'll create a specific amount of chlorine at equilibrium, which will be 1/2 the amount of the ClF3 that's reacted away. And in fact, for the fluorine that's formed, you're going to form 3 times as much fluorine as chlorine. And that's because the ratio of the products in the balanced equation is 1:3. So in grading this, I would want you to show that the amount of the reactant that reacts away is proportional to the amount of products that are formed in the ratio given by the coefficients in the balanced equation of 2 to 1 to 3. So the ClF3 decreases by a factor of 2, where the F2 would increase from 0 by a factor of 3, and the chlorine's concentration would increase by a factor of 1. And then when they reach a horizontal line, that's when their concentrations remain steady and you've reached equilibrium. Number 3, the reaction N2 plus 3H2 goes to 2NH3 is first order in nitrogen concentration and second order in hydrogen concentration. Write the rate expression for this reaction. So rate expression is an algebraic expression that tells what the rate of the reaction equals. And it's always going to equal a constant, which is proportional to the temperature, then multiplied by the concentrations of the reacting molecules, and their exponents are what we call the orders of the reaction. So the rate law for this reaction, rate would equal K times the concentration of N2 to the first power, because they said that nitrogen was first order, multiplied by the concentration of hydrogen to the second power, because they said that was second order. Number 4, for the reaction in question 3, if the initial reaction rate is 0.20 molar of N2 reacted away per minute, what would be the initial rate in molarity of hydrogen reacted away per minute and the molarity of ammonia formed per minute? So in this particular problem, for the same reaction, we're told that the rate of disappearance of nitrogen per time is 0.20 molar per minute. To calculate what the rate of disappearance for hydrogen would be, we're going to start with the number we have for nitrogen, 0.20 molar of nitrogen per minute, and use the coefficients in the balanced equation to convert from nitrogen to hydrogen, which is a 3-to-1 ratio. And if we do that, we're going to get the rate of the reaction in the molarity of hydrogen reacted away per minute, which should be 0.60. To calculate the molarity of ammonia formed per time, that's going to be starting once again with the molarities per minute, the rate of the disappearance of nitrogen, and then multiply by the coefficients in the balanced equation to give us the proper ratio between nitrogen and ammonia, which is a 1-to-2 ratio. 1 mole of nitrogen reacts away, it forms 2 moles of ammonia, or molar if you want to, and that's going to give you a final value for the rate of appearance of ammonia of 0.40 molar per minute. Number 5, for the reaction 2NO plus H2 yields M2o plus H2o, the following data was given and collected at the same temperature. This is going to be data for the initial rate of disappearance of NO, and then the concentrations initially of the NO and the H2, and there's 3 different trials. A says, what is the rate expression for this reaction, which is another way of saying what is the rate law. So to calculate this from these 3 different experiments, If we first want to determine what the rate law is going to equal a constant, which depends on temperature, multiplied by the concentration of each of the reactants in the chemical equation, which are NO and H2, but they're going to be raised to some specific powers, which are their orders, that we're going to determine experimentally. So if we want to calculate what the value for X is, the order for nitrogen monoxide, we need to pick two trials where hydrogen remains constant, and that would be the second and third trials. I'm going to take all the data from the second trial, and I'm going to plug it into the rate law. Then I'm going to take all the data from the third trial, plug it into the rate law, and divide by that. I'm doing the second trial divided by the third trial because I always want to have the trial with the highest initial rate on top. Now I divide this out. 0.72 divided by 0.18 is 4. The k's cancel out. 1.20 to the x divided by 0.60 to the x is 2 to the x. And 0.37 to the y divides out with 0.37 to the y. This simplifies to 4 equals 2x. X must equal 2. We now know that the reaction rate is second order in nitrogen monoxide. I'll put the 2 there for the exponent for the nitrogen monoxide. Now to calculate what y is, we need to pick two trials where the nitrogen monoxide concentration is constant, and that would be the first two trials. So doing the same technique, I'm going to take all the data from the first trial and plug it into the rate law. I'm going to take all the data from the second trial, plug it into the rate law, and I'm going to divide by that. When I divide this out, the left side of the equal sign becomes 2. The k's cancel out. The 1.2 to the seconds cancel out. And at the end, 0.74 to the y divided by 0.37 to the y is 2 to the y. So therefore, 2 equals 2 to the y. Y must equal 1. We now know the order with respect to hydrogen. That's going to be first order. So therefore, the rate law for this reaction is rate equals K times NO squared times H2 to the first. B says, what's the numerical value of the rate constant with its units? So to calculate this, or actually first, B actually said, what is the order of the reaction? Sorry. So the order of the reaction, we would say, is third order overall, but we would say specifically it's second order in nitrogen monoxide and first order in hydrogen. Now on to C, calculate the numerical value of the rate constant. I'm going to plug all the values from one of the three trials into the rate law and solve it for K. So if I solve the rate law for K, K will equal the rate divided by the concentration of NO squared multiplied by the concentration of H2. And if I pick all the data from the first trial, the rate is 1.44 molar per minute. The molarities were 1.20 and 0.74 respectively, and I have to square the molarity of the NO. In terms of the units, I have a molarity on the top and I have molarity cubed on the bottom, so the units will be molarity to the -2, including the minutes to the -1 because that doesn't cancel out with anything. So rounding to two significant figures because of the 0.74, I get 1.4 molar to the -2 minutes to the -1. D says what will be the initial rate in molarity of H2 per minute if the initial concentration of NO is 0.75 molar and the initial concentration of hydrogen is 0.75 molar. So I'm going to use the rate law and I'm going to use my value of K that I just calculated, and I'm going to put in the two initial molarities of the NO and the H2. So using a guard digit, the K was 1.35 molarity to the -2 minutes to the -1, multiplied by the molarity of NO, 0.75, and squared, and multiplied by the molarity of H2, 0.75. Units cancel out to leave molarity per minute, and to two significant figures, I get 0.57 molar per minute as the rate of disappearance of hydrogen per minute. E says what's going to be the initial rate of disappearance in molarity of NO per minute under the same conditions. So if we know the concentrations of the NO and the H2 are both 0.75 molar, and we knew the rate of the reaction in terms of disappearance of hydrogen was 0.57 molar per minute, if I use a guard digit, 0.569 molar per minute, I can use the balanced equation to convert this from the rate of disappearance of hydrogen to the rate of disappearance of nitrogen monoxide because they're in a 2-to-1 ratio. It's 2 moles of nitrogen monoxide reacting with 1 mole of hydrogen. So multiply that by that ratio, and the rate of disappearance of nitrogen monoxide will be 1.1 molar per minute. Number 6, for the gas phase reaction 2NO plus Cl2 yields 2NOCl, the following data was presented and collected at the same temperature. So we're given 3 experiments where there have been 3 different initial rates measured with the initial pressures of NO and Cl2 given. And the point of this is they can give you molarities or they can give you pressures, and we can still calculate a rate law based upon that. It says, since the pressure of a gas is directly proportional to the concentration of the gas, we can express a rate law for gaseous reactions in terms of partial pressures. So A says, what is the rate expression for this reaction? Well, that would be rate equals K times, and then we can use partial pressures. Partial pressure of NO to some unknown exponent X, multiplied by the pressure of the other reactant, Cl2, raised to some exponent Y. And to calculate those exponents, if we want to know X first, we've got to choose two trials where the partial pressure of chlorine remains the same. That would be trials 2 and 3. So I'm going to take all the data from trial 2, plug it into the rate law. Then I'm going to take all the data from trial 3, plug it into the rate law, and divide by that. On the left side of the equal sign, 0.040 divided by 0.010 comes out to be 4. The k's cancel out. The next factor turns out to be 2 to the x, and the last factor cancels out. So this simplifies to 4 equals 2 to the x. Therefore, x must be 2. And so this reaction must be second order with respect to nitrogen monoxide. So now the order of the nitrogen monoxide has been placed into the rate law. Let's calculate what Y is, and we're going to have to choose two trials where the pressure of NO stays constant. That would be the first and the third. And because the third trial has the higher initial rate, I'm going to plug the data from the third trial into the rate law first and divide it by the data from the first trial and divide by that. On the left side of the equal sign, we get 2. The k's cancel out, the 0.50 squareds cancel out, and the final factor there on the right side becomes 2 to the y. So 2 equals 2 to the y must therefore equal 1, and so therefore the exponent for PCl2 has to be 1. So the rate law is rate equals K times the partial pressure of NO squared times the partial pressure of Cl2 to the first. B says, what's the order of this reaction? It's second order in respect to NO, first order in chlorine, third order overall. We just add the two orders together to get that. C, calculate the numerical value of the rate constant with its units. So if we solve our rate law for the rate constant and take data from any one of the 3 trials, and I'm going to take data, let's see, from the second trial here, I'm going to wind up having 0.040 atmospheres per minute on the top. And I picked this trial because the numbers are really easy. Both partial pressures are 1 atmosphere. So the answer is going to come out 0.040. The units will be, because we have atmospheres on the top and atmospheres cubed on the bottom, it'll be atmospheres to the -2nd, and then minutes to the -1. So the rate constant 0.040, atmospheres to the -2, minutes to the -1. D, what's going to be the initial rate of the reaction in appearance of NOCl per minute if the initial pressure of NO is 0.75 atmospheres and the initial pressure of chlorine is 0.75 atmospheres. So I'm going to use my rate law. I've just calculated the constant, and I'm going to plug in the two partial pressures onto the right side of the equation. The constant's 0.040, and the partial pressures are each 0.75. I'll square the nitrogen monoxide partial pressure. The units cancel out to give me atmospheres per minute, and this comes out to two significant figures, 0.017 atmospheres per minute. That's how fast the NOCl is going to be produced per minute. And then finally, E, what will be the initial rate in the disappearance of chlorine per minute if the partial pressures of NO and Cl2 are both 0.75. So once again, if we already know what the rate of the reaction is with respect to one of the reactants or products, and using a guard digit, we've just determined in part D that you're forming 0.0169 atmospheres of NOCl per minute. I can now determine the rate of the reaction with respect to any other reactant or product by just multiplying by the mole ratio in the balanced equation. And between NOCl and Cl2, it's a 2-to-1 ratio. So 2 atmospheres of NOCl will be equivalent to 1 atmosphere of Cl2 in the production of the reaction. And this comes out 0.0084 atmospheres of Cl2 per minute as the rate of the reaction with respect to chlorine.